Welcome to the Joy of Architecture.
And hello. Today we're diving deep into something absolutely critical for building modern cloud-native systems. How they handle demand that bounces around like a pinball.
Exactly. We've been exploring a really insightful report that digs into the patterns for building systems that aren't just built to last, but are also designed to adapt, becoming resilient, flexible, and efficient even when the workload shifts dramatically.
Yeah, it's about navigating those unpredictable spikes without, crashing, and also handling quiet periods without running up huge unnecessary costs. The source material you shared gives us a fantastic roadmap for this.
So our mission in this deep dive is to pull out the absolute key insights from this report on the patterns that make systems scalable and elastic. Think of this as your shortcut to understanding the core techniques used to build systems that can genuinely flex with demand.
And the report starts right off the bat, highlighting a crucial distinction that's often misunderstood: scalability versus elasticity. While scalability is just about a system's ability to handle more work by adding resources which can be planned, or even manual elasticity is the automatic real-time adjustment.
That's the key, isn't it? The automation.
Mm-hmm.
Elasticity is about scaling out when demand rises and scaling in when it drops, all happening dynamically.
Yeah.
The report makes it super clear. If a system is elastic, it is scalable, but a scalable system isn't necessarily elastic.
Exactly. You could have a manually scaled system that's scalable, but totally lacks that elastic responsiveness.
And in the world of microservices, where you want each individual piece to potentially scale on its own,
Yeah.
that independent automated elasticity is absolutely vital for both performance and keeping costs in check.
For sure. It really unlocks the benefits of microservices.
All right, let's unpack the first major pattern the report discusses, one that's really foundational to cloud design: horizontal scaling.
Okay. Horizontal scaling, or, scaling out and scaling in, it's the approach where instead of making a single server bigger, you add more servers or instances to distribute the load.
This immediately screams stateless applications.
Pretty much. Yeah.
If your application instances don't hold unique session data, you can just duplicate them and spread the traffic around. Seems straightforward enough.
Precisely. The report emphasizes this is ideal for web and API services facing unpredictable traffic, stateless workloads, and microservices. It's also fantastic for high availability because if one instance fails, the others can just pick up the slack.
The big benefit the report highlights is that you get virtually unlimited scalability.
Right. Theoretically, you can just keep adding machines.
To handle more load.
Yeah, you can handle massive volumes. And the report notes that it can be more cost-effective over time, especially for variable workloads. If you're efficient at scaling in during quiet times, that's important.
And easier maintenance deployments too, maybe?
It often allows for that, yeah. Gradual updates and things.
But it's not without its headaches. The report points out the primary trade-off is increased management complexity.
Oh, yeah.
You're dealing with potentially dozens or hundreds of instances.
Absolutely. And that complexity requires robust infrastructure like load balancing to distribute requests and service discovery so instances can find each other. Network latency between nodes becomes a factor.
Right.
And as you said, handling stateful applications is a significant challenge. You must externalize state to a shared service.
Externalizing state, putting session data, shopping carts, whatever, into a shared database or cache is non-negotiable for effective horizontal scaling, according to the report. We have to hammer that point home.
It fundamentally unlocks the ability to treat all your application instances as like interchangeable cattle, not pets.
So how do people implement this? The report gives examples across the major cloud providers. On AWS, you're looking at EC2 auto-scaling groups combined with elastic load balancing, or ELB. They react to things like CPU usage to add or remove EC2 instances automatically.
And Azure has virtual machine scale sets, or VMSS, which manage groups of load-balanced VMs using Azure Load Balancer or Application Gateway. And Azure Autoscale, based on metrics or schedules, drives the scaling action there.
And on GCP, it's Google Cloud Managed Instance Groups, MIGs, paired with Cloud Load Balancing. Their auto-scaling can be triggered by CPU, HTTP load, specific cloud monitoring metrics, or even time-based schedules. Lots of options.
Conceptually, the architecture the report describes, and you can picture this from Figure 1, is requests hitting a load balancer, which distributes them to your application instances. An auto-scaling service is watching metrics, maybe CPU, maybe queue length. If they spike, it tells the cloud provider to spin up more instances, and the load balancer starts sending traffic to them.
And then when load drops, it shuts down the excess one.
Exactly. Scale-in is just as important.
Operationally, the report stresses several points. Load balancer configuration is critical for fair distribution. Service discovery is needed because instances appear and disappear dynamically.
Right.
State management, as we hammered on, is key for anything not purely stateless.
You also need to think about data consistency. If multiple instances write to a shared database, that can get tricky.
Yeah, concurrency issues.
And centralized monitoring and logging are vital across all those distributed instances.
Yeah.
Deployment automation is basically a must.
And don't forget, scaling in efficiently saves money. And you have to factor in the time it takes for new instances to start up and, warm up before they can actually handle requests. Cold starts can bite you.
Yeah, that warm-up time is a real consideration.
The best practices boil down to design for statelessness, automate everything, use managed cloud services whenever you can, implement solid health checks,
Crucial.
monitor the right metrics, and test how your system scales under load. Really test it.
And the anti-patterns are just as important to avoid. Don't try to scale stateful apps horizontally without externalizing state. Don't ignore database bottlenecks because you'll just move the problem downstream.
Right.
Avoid manual scaling like the plague. Don't set overly sensitive triggers that make your system flap, constantly scaling up and down.
That gets expensive too.
It does. And crucial for cost, always set maximum instance limits so you don't accidentally bankrupt yourself.
Good point. The report uses Netflix as the prime example here. Their famous migration from vertical scaling in their own data centers to a massive horizontally scaled system on AWS.
Yeah, legendary.
Using EC2, ELB, and auto-scaling was fundamental to handling their global user base and massive fluctuating streaming load.
And their adoption of Chaos Monkey, intentionally injecting failures to test resilience, is a sign of the operational maturity required to make horizontal scaling truly robust at that kind of massive scale.
Okay, so horizontal scaling is about scaling out, but the report also covers its counterpart, vertical scaling.
Right. Vertical scaling, scaling up or down, is the opposite approach. You take a single server or instance and increase its resources, more CPU, more RAM, faster disk. You make one machine more powerful instead of adding more machines.
The report notes this is applicable for applications that are hard to distribute, and the classic example is of many traditional relational databases, right?
Exactly. Or systems where the bottleneck is really just that single node's capacity. It's also simpler if you just need a bit more power on a single node, or when simplicity is preferred and managing fewer instances is easier.
Yeah. Or if your application simply wasn't built for distributed computing and maybe refactoring isn't an option right now.
True. It's often the easier path for predictable growth on a single powerful server.
The benefits sound like simplicity initially, a straightforward performance boost for single node bottlenecks, and often you don't need to change your application code at all, which is a big plus sometimes.
True, those are the upsides. But the report is clear about the significant trade-offs. You're fundamentally limited by the maximum size of a single server. There's a ceiling.
Right.
And at the high end, this can become incredibly expensive. Those monster instances cost a lot.
And the big one, which the report really called out, is that scaling up often requires downtime. You typically have to stop the instance, change its size, and restart it.
Exactly. That downtime is a major operational consideration, especially for critical systems. And provisioning for peak load on a single instance means you might have significant resource underutilization most of the time. Wasted money.
Plus, it creates a single point of failure that one big server goes down, your service might be completely gone.
Yeah, that's a big risk.
The report gives examples on the cloud providers. On AWS, it's changing an EC2 instance type or scaling up an Amazon RDS database instance. Both usually involve a stop and restart.
Azure is similar. Resizing a virtual machine, a VM, typically requires stopping the VM, selecting a new size, and starting it up again. Downtime again.
And GCP, too. Changing a Google Compute Engine VM machine type usually means a stop restart. Although the report mentions disk size increases can sometimes happen live, which is a useful detail.
Right.
But generally, expect a restart.
The architectural sequence, conceptually shown in Figure 2, is straightforward, but highlights that restart. Monitor vendor risk, identify need, schedule maintenance, hopefully. Stop instance size, modify resources, start instance size, verify. The downtime is kind of baked in.
Operational considerations are dominated by that downtime, hitting the physical limits of a single machine, the high cost of the largest instances, and managing that single point of failure risk.
The best practices emphasize understanding when vertical scaling is appropriate, often for hard-to-distribute apps or databases. Monitor resources, plan carefully for downtime, and automate the stop resize start process where feasible to minimize the pain.
Anti-patterns include defaulting to vertical scaling for every problem, trying to scale up indefinitely without optimizing your application first.
Yeah, optimize first.
Ignoring the single point of failure risk and frequent manual resizing, which might indicate you should really be considering horizontal scaling instead.
And the report presents the Stack Overflow case study as a great example that vertical scaling isn't dead. They use powerful vertically scaled SQL Server machines for their database layer, prioritizing simplicity and optimization there.
They make a key point the report highlights. Databases often scale up while applications scale out, with the state externalized to the database, enabling the application tier to scale horizontally effectively.
It's a common pattern, that hybrid approach. Vertical scaling definitely still has its niche.
Moving from manual scaling, which both horizontal and vertical approaches can be, to making systems truly elastic requires automation. And that brings us neatly to auto-scaling.
Right. Auto-scaling is really the engine of elasticity. It's the dynamic, automated allocation and deallocation of cloud resources based on predefined conditions like traffic, utilization, or maybe just a schedule. It takes the manual effort out of responding to load changes.
Exactly. The report stresses this is primarily applied to horizontal scaling, though sometimes you see nuances with things like Lambda memory. It ensures you always have the right resources for performance and availability. And crucially, it helps minimize costs by scaling down when demand drops. That scale-in part is key.
Absolutely. This is applicable for pretty much any variable or unpredictable workload web apps with traffic spikes, microservices that need independent scaling, or batch jobs that only run sometimes.
The benefits are clear. True elasticity matching demand, enhanced availability by adding capacity and replacing unhealthy instances.
That's a big one.
Significant cost optimization by scaling down, consistent performance, and dramatically reduced manual operational effort. Seems like a win-win.
Mostly, yeah. But the trade-offs involve configuration complexity. Defining the right policies and thresholds is key and can be tricky. If policies are too sensitive, you get flapping instances constantly starting and stopping.
Right, instability.
And you risk over or under provisioning if it's misconfigured. Plus, you still have to account for the time it takes for new instances to launch and be ready to handle traffic during a scale-out event.
That launch time again.
Yep.
The report shows this is standard across the board. AWS Autoscaling works with EC2 Autoscaling groups, ECS, DynamoDB, Aurora, lots of services. Azure Autoscale works with VMSS, App Service Plans, GCP Autoscaler with MIGs. They all have it.
And they offer different policy types, as the report details. Scheduled scaling for predictable spikes, like holiday sales. Dynamic or reactive scaling based on real-time metrics, like target tracking, which aims to keep a metric like average CPU utilization at, say, 70%.
Right.
And predictive scaling, which uses historical data and ML to forecast demand and scale proactively, trying to get ahead of the curve.
That predictive stuff sounds cool, but probably complex to set up right.
It can be, yeah. Needs good historical data.
The generic architectural sequence, like in Figure 3, is monitoring collects metrics, autoscaling engine checks policies. If threshold crossed, instance management adds or removes instances, load balancer gets updated. A cooldown period follows to prevent those rapid cycles, the flapping.
Operationally, the report emphasizes choosing the right metrics that actually reflect user experience or system health, not just CPU. Maybe requests per second per instance or queue depth.
Good point.
Tuning thresholds is an art and science. Cooldown periods are essential to prevent flapping. You must account for instance launch time, and warm-up things like warm pools or predictive scaling can help mitigate that delay. Robust health checks are vital for detecting bad instances.
And cost management. Setting maximum limits prevents runaway costs. Don't forget that.
Absolutely critical. And you need to consider stateful apps carefully and ensure downstream dependencies can handle the scaled load. Test your policies.
Best practices highlighted. Use target tracking policies if your cloud offers them. They're often simpler and effective. Choose metrics wisely. Set appropriate cooldowns. Implement graceful shutdowns for scale-in, letting instances finish current requests. Use multiple availability zones for resilience. Monitor the auto-scaling events themselves to see what it's doing. And right-size your instances before relying only on scaling the number.
and the anti-patterns. Scaling on inappropriate metrics, like disk I/O if you're CPU bound, having conflicting scalars fighting each other, common gotcha in Kubernetes, aggressive thresholds or short cooldowns leading to flapping,
Right.
ignoring instance warm-up time, not setting maximum limits, hello, unexpected huge bill, scaling based on unreliable health checks, and thinking auto-scaling will magically fix poorly written, inefficient application code. It won't.
Yeah. Garbage in, scaled garbage out.
Pretty much.
Case studies back this up. An ad tech platform on AWS used auto-scaling based on request volume and time of day for both performance and cost optimization, even integrating with external monitoring like Datadog.
An e-commerce company migrating to Azure Kubernetes Service, AKS, used Azure Load Balancer and Autoscale to achieve high uptime during peak seasons and saw significant cost savings by dynamically adjusting infrastructure.
Airbnb on AWS is another classic, using EC2, ELB, and autoscaling to handle massive fluctuations in travel demand. It's core to their operation.
The report mentions monitoring specifics too, like tracking CPU, memory, disk, and network usage via Azure Monitor for VMSS, or vCPU and network throughput for GCP MIGs, showing how detailed monitoring is needed to verify and refine those scaling rules.
Okay, next, the report looks at a pattern designed specifically to handle sudden, unpredictable spikes and decouple components. Queue-based load leveling.
Queues, a classic decoupling pattern. This uses a message queue as a buffer. A service that produces tasks, the producer, sends them to a queue, and a separate consumer service processes them from the queue at its own pace.
This is incredibly effective for decoupling, isn't it? The producer doesn't need to know if the consumer is busy, slow, or even temporarily down.
Exactly. It just puts the message on the queue and moves on. It smooths out load spikes beautifully because the queue absorbs the burst.
So it's ideal when services face intermittent heavy loads. Tasks can be processed asynchronously. You don't need an immediate response.
Right.
And a producer and consumer rates might differ or be variable.
The benefits are clear. Improved system availability because the producer isn't blocked by the consumer. You can scale producers and consumers independently based on their needs. Enhanced resilience because messages persist in the queue if the consumer is down. It smooths out spikes for consumer stability. And you can potentially provision consumers for just the average load, not the peak, which can save significant costs.
The main trade-off is introducing a new component, the queue itself, that you have to manage, monitor, and pay for.
Right. And scaling the consumers based on queue depth adds its own layer of complexity. Message ordering can be a concern. With standard queues, they typically offer at least once delivery, but best effort order. If order matters, you need FIFO queues, which have their own considerations.
And it inherently introduces latency. Tasks aren't processed immediately.
Correct. It's asynchronous by nature, and there's the cost of the queue service itself, which can add up at high volumes.
The report highlights that the queue must be able to handle the bursts, and monitoring queue depth is absolutely vital to know if your consumers are keeping up. A constantly growing queue is a major warning sign.
Definitely. Real-world examples are everywhere. AWS SQS Simple Queue Service, both standard and FIFO, is a go-to for decoupling in microservices and serverless architectures. Consumers like EC2 instances or Lambda functions pull the queue.
Azure offers Azure Service Bus, which has more enterprise features like FIFO, sessions, dead lettering, transactions, or the simpler Azure Queue storage. Consumers can be Azure functions or container apps, often auto-scaling based on queue length. Service Bus is often preferred for more complex load leveling.
And GCP has Cloud PubSub, a highly scalable asynchronous messaging service. Works great as a buffer. Consumers are services like Cloud Functions, Cloud Run, or GKE subscribers.
The architectural sequence, like in Figure 4, is conceptually simple. Producers send messages to a message queue. The queue holds them reliably. Consumers retrieve messages, process them, and then acknowledge them, which removes them from the queue.
And importantly, the number of consumers can be dynamically scaled based on how many messages are waiting in the queue. That's often tied into autoscaling.
Operationally, the report stresses monitoring queue metrics. Queue length is the big one, but also things like the age of the oldest message. How long are things waiting? And the size of your dead letter queue, or DL queue.
Yes. DL queues are crucial. They catch messages that consistently fail processing so you can investigate without blocking the main queue.
You also need to monitor consumer health, ensure message durability settings are right for your needs, and design consumers to be idempotent.
Right, idempotent is key. It means if a consumer accidentally processes the same message twice, which can happen with at least once delivery guarantees. It won't cause negative side effects like charging a credit card twice.
Good example. Configuring visibility timeout correctly is also important. That's how long a message is hidden while a consumer works on it. Too short, and another consumer might grab it. Too long, and it takes ages to retry if the consumer fails.
It's a balancing act.
Best practices. Decouple services asynchronously with a queue. Scale consumers dynamically based on queue length. Implement idempotency in consumers. Use DLQs religiously. Actively monitor queue metrics. Choose the correct queue type, standard versus FIFO. Control consumer processing rate. Handle poison pills, those messages that always fail.
Anti-patterns. Processing synchronously despite using a queue defeats the whole purpose. Ignoring queue buildup until it explodes. Not using DLQs, losing failed messages. Non-idempotent consumers with at least once delivery.
Risky.
Or just moving the bottleneck downstream without fixing it. Using a single large queue for totally different task types, which can lead to head-of-line blocking.
Case studies include academic research showing the math behind queuing systems, or practical examples like an Azure exam scenario using Service Bus for high-volume agricultural requests.
A fantastic large-scale example the report touches on is Uber. They use queuing extensively for ride matching and dispatching to smooth the incredibly dynamic supply of drivers and demand from riders.
Makes sense.
The report also mentions benchmarks showing even SQS FIFO can achieve high throughput with careful design using message group IDs and highlights key monitoring metrics for service bus performance and pub sub latency.
Okay, sometimes tasks aren't just spiky, they're genuinely long-running. That leads us to the asynchronous request-reply pattern.
Right. This pattern is specifically for operations that take a significant amount of time, seconds, minutes, maybe even hours. The client sends an initial request, gets an immediate acknowledgement back, usually an HTTP 202 accepted response.
Got it.
And then pulls a separate endpoint later to check the status or retrieve the final result once it's ready.
This is essential for client applications that can't afford to just block and wait, like browsers or maybe mobile apps, or when integrating with systems that don't support modern callbacks or long-lived connections.
Exactly. It effectively decouples the front-end client from slow back-end processing. The back-end can take its sweet time without the client hanging.
The key benefits highlighted in the report are client responsiveness. They get that immediate 202 answer, independent back-end scalability for the workers doing the long task, and resilience, as the long task is often queued up. If the worker fails mid-process, the request isn't lost, it can potentially be retried.
But it definitely adds complexity, particularly on the client side, which needs logic to handle the polling. When to poll, how often, what to do with the status.
Yeah, and critically, the status endpoint itself can become a bottleneck if you have a high volume of clients polling frequently.
No, absolutely.
The report stresses that this endpoint needs to be highly scalable, often relying heavily on caching to avoid constantly hitting the underlying status store.
Overall system reliability also depends on multiple components working together. The initial API, the queue, the worker, the status store, the status endpoint. Lots of moving parts.
And polling itself can be inefficient. Lots of requests that might just get back still pending.
True. The report mentions that orchestrating these multi-step asynchronous workflows can be simplified by using dedicated tools like AWS Step Functions, Azure Logic Apps, or Durable Functions, or GCP workflows. They help manage the state and flow.
The implementation often combines several services. On AWS, you might see API Gateway or Lambda for the initial endpoint, SQS for the queue, maybe EC2, ECS, or Lambda as the worker processing the long task, DynamoDB to store the job status, and S3 for the final results if they're large.
Azure examples use API management or functions for endpoints, service bus or queue storage for the queue, functions, web jobs or containers for the worker, table storage or Cosmos DB for status, and blob storage for results. Very similar pattern.
And on GCP, cloud endpoints, API gateway, functions or run can serve as endpoints, PubSub for the queue, functions run or GKE for the worker, Firestore or data store for status, and cloud storage for results. The components vary, but the pattern is the same.
The typical HTTP polling sequence described is client posts his request, API validates, creates a job ID, sends a message to a queue, saves an initial pending status. API returns 202, accepted with a location header pointing to the status URL, maybe a retry after header suggesting when to poll next.
Okay.
A worker picks up the message from the queue, processes the task, updates the status in the status store, processing then completed or failed. The client periodically gets the status endpoint using that location URL.
And the status endpoint just queries the store.
Right. If pending or processing, it returns 200 OK with the status and maybe another retry after. If completed, it returns 200 OK with the results or a link to them, or maybe redirects 302 303 to the results. If failed, it returns an appropriate failure response.
And the client keeps polling until it gets a final state.
Yep. Caching on that status endpoint, again, is crucial because it gets hit repeatedly by potentially many clients.
Operational considerations include ensuring the status data store is reliable and scalable, that the status endpoint itself can handle high polling load. Designing a sensible client polling strategy, exponential backoff, is a must. Don't just slam it every second, and respect that retry after header if provided.
You also need to manage job timeouts. How long should a job run before we give up? And client polling timeouts have robust error handling in the worker and secure both the status and result endpoints. Don't leak data.
Good point. And make the worker idempotent if retries are possible. Maybe offer cancellation.
Cancellation is often a good idea for long tasks, yeah.
Best practices from the report. Always return HTTP 202 immediately for long tasks. Provide the location and retry after headers. Use a message queue for decoupling the work. Maintain clear job states. Ensure the status endpoint is fast, uses GT and only query status. Secure access. Implement robust error handling everywhere.
And consider alternatives like WebSockets or server-sent events, SSE, or webhooks if true real-time updates are needed, and you can handle the added complexity compared to simple polling.
Anti-patterns. Blocking the client instead of returning 202. Having unreasonable polling intervals or no retry after header. Having the status endpoint do the actual work instead of just reporting status, bad idea. Inconsistent HTTP codes. Insecure endpoints. No job timeouts. And overly chatty status updates that aren't really useful.
Case studies include the classic e-commerce order processing. You get an immediate order placed message, like a 202, and you can check the order status later while payment, inventory checks, and fulfillment happen asynchronously in the background.
AWS Lambda's own asynchronous invocation model uses this pattern internally. You call Lambda async, get a 202 back, and Lambda handles the queuing and retries behind the scenes. The report mentions challenges there like noisy neighbors in the shared infrastructure and solutions like shuffle sharding.
Azure functions triggered by service bus are often the workers in this pattern, and the report emphasizes correct async-await handling in your function code for reliable message processing. Don't block the thread.
And on GCP, while Cloud Functions or Run can handle the API polling endpoints for really long tasks, maybe hours long, the report notes the worker function might just delegate the heavy processing to other services like GKE or Vertex AI, orchestrated perhaps by cloud workflows. The pattern supports that delegation.
Yeah, it's flexible.
Finally, the report tackles how to protect your services from overload, especially public-facing APIs. That's throttling.
Right, throttling, often called rate limiting, although there can be subtle differences. It's about controlling resource consumption by limiting the number of requests a client can make within a specific time window.
So if they exceed the limit?
Requests are rejected, usually with an HTTP 429 too many requests status code. Sometimes they might be delayed or queued, but rejection is common.
This seems essential for public APIs to ensure fair usage and prevent any single noisy client from hogging all the resources.
Absolutely. It also protects your backend services from sudden traffic spikes or even basic denial of service attacks.
And helps with resource and cost management, right? Enforcing SLAs for tiered access premium users, get higher limits maybe.
Exactly, and it improves overall system stability by preventing overload.
Benefits include system protection, ensuring fair usage, security against dams, predictable performance for well-behaved clients, cost control, and enabling API monetization through different access tiers.
The main trade-off the report points out is that if configured too strictly, it can block legitimate traffic. That's a balance. Sophisticated attackers might find ways around simple throttling methods.
And clients must be designed to handle the 429 response.
Critically, they need to implement retries, usually with exponential backoff and maybe some jitter, and respect the retry after header if the server provides one. Implementing distributed throttling accurately across multiple instances can also be complex.
It's definitely a balance between protecting your system and not unfairly penalizing your users.
Cloud providers offer layered throttling. AWS API Gateway has regional, account, API and client-level throttling using things like usage plans and API keys. It often uses a token bucket algorithm, which allows for small bursts. AWS WAF also has rate-based rules often based on IP addresses.
Azure API management uses flexible, policy-driven throttling rate limit by key or quota by key policies, where the key can be an IP, subscription key, or some custom expression. Azure Application Gateway WAF and Front Door WAF provide edge rate limiting. The report notes that in distributed systems, throttling can have some imprecision due to coordination latency.
Yeah, perfect accuracy is hard.
GCP Cloud Endpoints offers quotas per minute per project or method, though the report mentions a roughly 30% error margin due to how they aggregate data. Cloud Armor provides rate-limiting rules for DDoS protection at the network edge. The report briefly mentions common algorithms like Token Bucket allows bursts, and Leaky Bucket smooths the rate.
The architectural flow, like in Figure 5 is, client sends request check API gateway or some throttling logic, intercepts checks limits based on client identity. If within limits, request goes to the backend. If it exceeds, it's rejected. Typically with HTTP 429, often with a retry after header, telling the client when it's safe to try again.
And the client needs to handle that 429 gracefully and back off.
Operationally, critical points include managing distributed counters if you build it yourself. It needs a fast, shared store like Redis with atomic operations. Ensuring the throttling check itself is extremely low latency. Managing complex configuration policies, monitoring 429 errors, and request rates very closely.
Right, you need to know if it's working or blocking too much.
Understanding the accuracy versus performance trade-off, clearly communicating limits to clients via documentation and headers, deciding on burst allowances, choosing the right identification key, API key or user ID is generally fairer than just IP, and potentially dynamically adjusting limits based on system health.
Best practices. Communicate your limits clearly through documentation and standard HTTP headers like X-rate limit, X-rate limit remaining, X-rate limit reset, and retry after. Throttle based on client identifiers like API keys or user IDs for fairness. Implement granular limits, maybe different limits per endpoint. Use managed API gateways when possible. Design client applications to handle 429s with smart retries, and monitor your throttling effectiveness.
Anti-patterns to avoid. Silent throttling, where you just drop requests without a 429, very frustrating for clients. Overly aggressive limits that choke legitimate use. Inconsistent enforcement. No burst allowance. Token bucket is generally better. Throttling without monitoring. Relying solely on IP address throttling, which is unfair to users behind NATs or proxies, and clients that ignore 429s and just keep hammering you.
Case studies include the Twitter API, a classic example with strict tiered rate limits per endpoint and per user token, requiring clients to handle 429s properly.
AWS API gateway discussions often highlight the token bucket burst behavior and the importance of understanding its layered limits, usage plan, stage, account, regional.
Azure API Management's policy-based approach is noted for flexibility, but also that acknowledged imprecision in distributed environments.
And the most striking case study referenced is from GCP Cloud Endpoints. While it offers quotas, a case involving a massive bill incurred due to a compromised API key starkly highlights that throttling and quotas are essential, but they must be combined with robust API key security and vigilant billing monitoring to prevent absolute financial disasters.
Wow. A crucial reminder that these architectural patterns exist within a broader operational and security context. You can't just focus on the tech.
Absolutely, it all fits together.
Okay, wow, that was a deep dive into 6 powerful patterns. Horizontal scaling for scaling out stateless apps, vertical scaling for scaling up single instances, auto scaling for automated elasticity, queue-based load leveling for buffering spikes and decoupling, asynchronous request-reply for handling long tasks, and throttling for protection and usage control.
The report really brings it all together, showing that no single pattern is a silver bullet. They are often combined, and successful implementation hinges on leveraging managed cloud services, implementing comprehensive monitoring, and truly understanding the specific needs of your application and its workload.
And the cross-cutting themes, striving for stateless design where possible, embracing automation at every level, and building in observability are absolutely critical, regardless of which specific pattern you're applying. They underpin everything.
Looking ahead, the report touches on interesting future trends. AI-driven predictive scaling getting more sophisticated, the evolution of serverless phase towards finer-grained elasticity and maybe even more stateful capabilities, enhanced Kubernetes auto-scaling, like KEDA for event-driven scaling, becoming standard.
Yeah.
Chaos engineering becoming a regular practice to actually test these resilient systems, and the increasing integration of FinOps financial operations to understand the real-time cost implications of your scaling decisions.
That FinOps point is fascinating, isn't it? Elasticity is sold partly on cost savings by scaling down, but understanding the actual cost dynamics of your chosen scaling patterns requires dedicated effort and visibility.
It's becoming a critical part of cloud architecture, not just finance.
It's a continuous learning curve.
For sure.
So, based on the report, our key takeaways for you, the listener, are: design for statelessness whenever feasible. It simplifies so much. Automate everything you can: provisioning, deployment, scaling. Lean on those managed cloud services offered by AWS, Azure, and GCP. They do a lot of the heavy lifting for these patterns. Implement comprehensive monitoring and observability. You can't manage what you can't see. Don't be afraid to combine these patterns strategically. Test rigorously, including stress testing and maybe even chaos engineering. Focus on cost optimization by ensuring you scale down effectively, not just up. And educate your teams on these fundamental architectural principles.
Building truly scalable elastic systems is complex, no doubt, but these patterns provide proven approaches and a solid foundation.
Absolutely. And speaking of continuous learning and those future trends, we talked about how critical monitoring is, not just for performance, but also potentially for cost, with that FinOps angle.
Right.
Given the complexity and the direct cost implications, could FinOps become not just a budgeting tool, but maybe the next layer of architectural mastery, where architects are judged not just on system uptime and throughput, but on delivering that performance at the optimal cost, by truly mastering elasticity and its financial impact? Something to think about.
A very pertinent question for the modern cloud architect indeed, where architecture meets the bottom line.
That wraps up this deep dive into architectural patterns for scalability and elasticity. We hope this exploration of the report's insights gives you valuable knowledge for building resilient cloud systems.
Stay informed. Keep experimenting with these patterns in your own architectures and see what works best for your specific context.
And be sure to subscribe to Joy of Architecture wherever you listen so you don't miss future deep dives.